Again, thank you very much for the invitation, and it's an honor to be here as a distinguished lecturer. And I gave a lecture on Tuesday that was sort of motivation for the lecture I'm going to give now. And I'm doing something that I don't think I've done before. And Burke especially wanted sort of the most recent results, right? So I finished this paper in the wee hours of Wednesday night, Thursday morning. I tried to get it on the archive, but something went wrong, so it didn't appear this morning. But as I mentioned before lunch, it's the first one on my list of publications, which is this website here, if you click on publications. So this work is work that happened, that we sort of figured out how to do it about 6 weeks ago in Bristol. And I'd say all the work has really been done in collaboration with Michael Berry. Okay, so the ingredients are, so these are the things I want to sort of convey. And perhaps the most important thing is the framework that I'm going to use to address the questions I'm going to address, right? I think it's a very crude, simple version of something much more general. And I'm going to introduce an exact formula for the sum of eigenvalues of single particle states, how you can think about them. So previously I introduced these same spin non-interacting fermions. So if we take so I'll be talking about potentials that look like this. I will choose the 0 to be the bottom of the potential. And then if we think of fermions in such a potential, well, if I have 10 fermions, they'll occupy the lowest 10 levels. And their total energy will be the sum of the 10 lowest eigenvalues. The H-bar expansion, we'll see, is sort of related very closely to the gradient expansion. Now, everything I'm going to talk about, pretty much everyone in this room will have done a calculation of this kind in a much more sophisticated setting. But think of this, so what I've done is I've found, I think, the simplest possible setting in which I can address these questions. And so this should be a simplification of your own work. And I apologize in advance. I won't make all the relations to everything we've heard about for the last 2 weeks. It's just because there are too many of them. And I'm going to derive the form of correction to the gradient expansion. I'll give a few numbers, and I'll talk a little bit about the implications. So the inspiration, in a sense, for this is you have to start from the I'll call it WKB0, meaning whenever it was, the classical action quantized is that simple formula. I'll show it. It'll come up a lot. Then there's also the WKB expansion. So it's actually the 0 order term in an H-bar expansion, and you can get an expansion for the action. And in fact, I'll talk about a quantum action. And actually, this quantum action is shown here. I imagine a function of energy. So epsilon will be my energy. This is this quantum action. And the definition is simply going to be that it's a smooth monotonic function which at the half integers matches the eigenvalues of my potential. That's my defining characteristic of this thing. Now, a little more realistic motivation, right? As I've been trying to emphasize over the last week or so, to me, the crucial aspect of why density functional theory has been so successful is this gradient expansion that got generalized first in 1968, but then the modern ones came along in let's say, the mid-90s. I was involved in one of the more popular ones, and Weitao Yang was involved in the other one. By the way, just as a marketing tool, it's really important to make sure that there's at least two competing versions of a formula so that people have to cite which one they used. But this procedure is not derived, right? The fact that we even have two of them tells you that. Whitehouse is typically at least a factor of 2 more accurate for thermochemistry, right? This is this Li-Yang-Par correlation function, factor of 2 more accurate than PBE. So, and typically for binding energies in molecules, either of them are, PBE is about 3 times more accurate than LDA, and LIP is about 5 times more accurate. So you get improvements over the local density approximation. So that's all I'm going to say. And in my first lecture, I talked a lot about simplifying the problem, and we're going to go and just look at the kinetic energy of these non-interacting electrons. So the point is to find the mathematical framework in which one can understand why the functionals that are used in these 40,000 papers a year have the gradient of the density in them, right? Now I'm going to talk a bit about this Poschel-Teller potential. I'll give you the formula in a minute. And actually here I found this old figure from one of my students in their notes, but actually we'll start the zero of the potential will be at the bottom of the well, and we'll go up. And here we just put in, this is a well that holds 3 levels, and you see that these dashed lines are the Thomas Fermi density. And as I put 1 particle, 2 particles, 3 particles, the quantum oscillations are a little funny in this case, but you see it's doing this weak approach to the Thomas Fermi density, right? So that's that Lieb-Simon limit. But the point will be to go past the Lieb-Simon limit for this very simple problem. Okay, so I've mentioned the zero of the potential will be at the bottom of my well. So I'm not talking about the Coulomb in this case. The eigenvalues we count starting with, so here's the Schrodinger equation, and I'm going to start counting by 1, 2, 3, right, instead of 0, 1, 2. And that way, when I have m particles in the well, it's m levels that are occupied. That's a little unusual. I'm going to use Hartree atomic units. H bar and m are going to be 1. But I'll use this parameter eta as a dimensionless measure of h bar. So I'll be looking as h bar goes to 0. And as I said, right, the sum of the eigenvalues. Everybody with me so far? Okay, thank you. If David's with me. Okay, more background, right? So the gradient expansion, that is the starting point of these sort of modern functionals, right? We have a simple version in 1 dimension. So this n0 is the leading order, and it's just proportional to pf. And then the kinetic energy is pf cubed, right? And then when we do density functional theory, we feed one of these into the other, and we get this. So this is the Thomas Fermi expression for same spin non-interacting electrons in 1 dimension. And we've seen this very often with n to the 5/3 in 3 dimensions. But there's a nice paper by Samaj and Purkis in which they sort of generate the expressions for this to all orders. And so the next order, which is the only one that we'll consider most of the time, you can figure out what so this is the density as a functional of the potential, right? And I notice I'm missing a formula. This PF is the classical momentum at a given point in space, and this is the Fermi energy. And that'll be or we could call this the chemical potential in this case, and that's determined by the integral of the density over all space being equal to the number of particles, number of occupied levels. And let me write this as the real part of this, so that it's just 0 So this is positive in a classically allowed region, negative in a forbidden region. So when I put in the second order expansion, and again I do this gradient expansion, I assume these are derivatives of the potential with respect to space. I assume these are small, so I feed this one into that one, and I get this minus 1/3 of the von Weizsäcker. So these are easily derived. You can do linear response, for example, or you can read this paper, which does it in a very elegant way. Okay. And I had mentioned on Tuesday that Walter Cohn always emphasized asking the right question, right? Lots of really bright people here in this room, right? There are lots and lots of really hard questions, but ask the right one. And that was more important than figuring out the answers often was figuring out which question to ask. But in this case, I've told you I've been working on this problem for about 13 years, right? So it's no good. I did ask the right question. I just wasn't smart enough to answer it. So I asked lots of other people, and finally, my corollary is ask the right person the right question, right? And I finally did, right? It took me a while to realize who that person was. And here he is, right? So this is Michael Berry. He's at the University of Bristol. He'd helped out a little bit, as I'd mentioned, in some of the earlier projects, and I had this opportunity to go there for 5 months, which I did. I just came from there a couple of weeks ago. And I can say that, it's been one of the highlights of my scientific career learning from this gentleman. And he's been extremely kind and patient with me. And yeah, well, I'll give you some sense of what's come out of this. Okay, so staircase functions. So a lot of what I'm going to talk about is familiar to people who study semi-classical problems. And so I'll show you what we do. So this is the staircase function. So this is the number for a given epsilon, how many levels are below that epsilon, right? So if and then this S is shown here. This is just summing up the levels, multiplying by the energy, right? So again, as a function of energy, it tells me what the sum of the energies are below the energy I look at. So this one looks like this, right? It's the energies, and each time you go up, it adds one more eigenvalue. Very simple. And n sub e means exact. Now, I've already told you about this guy here, right? And so the crucial trick here is going to be, we have this guy, and I've set it equal to j minus a half. The half is coming from, if you know these things, from the Maslov index for the turning points on either side of the potential. Okay, but that's, essentially looks like a convention. So I use j bar to mean j minus a half. And now I'm also going to turn on the temperature just a little bit. And this is important because these functions are not invertible as they stand, right? But if I turn on just a tiny amount of temperature, then they all get rounded off, and then I can differentiate them and I can invert them at my leisure. So I'll put in a Fermi factor. And of course, the things I'm going to tell you about are actually all true at finite temperatures, but I don't want to get into that. Here, for now, it's just going to be a device so that we can invert functions. Okay, so if you know this guy here, right, then you can deduce what the number staircase is. It's just this thing called a floor function, right? And the floor function is just if I take x, the floor function is the highest integer below x. Right? So it just steps up by 1 every time x crosses an integer. It's that simple. And yes, the notation I'm using is all learned from your book. Right? So if I take the floor function for this guy, so actually if I add half to x, then it gives me the nearest integer, right? So the floor function for this guy is going to be, I'm going to go like this, I'm going to go up, and at each eigenvalue I step up like that, right? And this is our floor function. And I put a beta there to remind myself that I've turned on the temperature just a little bit so that I've smoothed out those functions. Now, I'm sorry I didn't have time to prepare too much of this talk, so I only have a couple of proper figures. This is one of them that I sort of highlighted. And so, in fact, I was supposed to use black for my number staircase. And the difference between the two, I use these sort of angle brackets as a sawtooth, taken from Burke's book, is a sawtooth function which goes just steps from sort of 0 up to a half, drops down, and then goes from 0 to a half. It's periodic. I should draw that one because it'll be important. So this, I'll call it y here, just looks like this. And it drops at a half, crosses 1, 3 halves, and so forth. And it goes up to a half. It's just, this is just a linear in y there. And here, you know, it's plotted as a function of the energy. I is a function of the energy. But it separates, so knowing I of epsilon, right, I can get the number staircase. And so I of epsilon is a smooth curve, but it's very important to understand that I chose I of epsilon. So there are many choices of smooth curves in the semi-classical literature. Once I've chosen it, though, then the red curve and the blue curve are determined. And of course, their sum is always the black curve, no matter what, as long as it hits the eigenvalues in the right place. Okay, so then we want to get the sum of the eigenvalues, the energy staircase. And what we can do is, once we've turned on the temperature, we can invert the function. So the mu of, so I use the script n for a continuous particle number, which I'm allowed to do. And mu of n is the inverse, let's say mu beta of n is the inverse of n beta of epsilon. And of course, mu of n is actually the chemical potential. That was discussed quite a bit earlier. And a crucial part to understand is that you must really turn the temperature, you must do some regularizing procedure, turn the temperature on, and then take it to 0 at the end in order for everything to be well defined. And then what you really want, of course, is the sum of the eigenvalues as a function of n. And so you can just feed in the inverses, and you find this very simple formula, and I'll show you pictures of it, that the sum of the eigenvalues as a function of n is just this. You know, the slope of it is equal to the first eigenvalue here, and then the sum of the eigenvalues there. It just goes linear with n. And of course, this is exactly the analog of the pictures that Whitehow and others have shown for, you know, this is the derivative discontinuity and all those things. But in a much simpler context, this is just non-interacting particles, right? But none of these discontinuities occur if I have a little finite temperature, everything is rounded off. Now, once we do that, we can then look at what is the formula for this S of n, right? Now, and you can take your I of epsilon, and an important feature that we'll introduce is this j, which is the integral of I up to some point, and this is a natural object introduced because you want the sum. And we also define this g of epsilon, which is the integral of this guy up to a given energy. And see that first formula there, it's trivially given by the floor function on I of I plus a half. So when we look at this guy, we can write him as a smooth part. The x part is just this j. And then there's this other piece, which is the sawtooth part, which goes into this g of, and when we write g as a function of n, we do the inversion and do the integral over 0 to n. We change variables from epsilon to n. And so we have this, I call it a discontinuous piece. This should be written as a function of a continuous n. It jumps in such a way, it jumps. This guy is smooth, but you also have this one here, and it jumps too in such a way as to produce exactly this straight line behavior in between. So this is all just, rearranging the functions, right? The important point, though, is here in the middle. When n is at an integer, this sawtooth guy is exactly 0, right? Whenever it crosses an integer, it's exactly 0, which means at the integer values, we don't have to worry about the sawtooth guy, right? He doesn't contribute. So which means in that middle formula, I didn't arrange them in a great order here, the middle formula for S of n, instead of putting mu, the chemical potential, in the exact inverse, I can just put in epsilon n, the smooth guy. So at the integers, I will always get the right answer. I won't be correct off the integers, but for any integer, and if I just want to get the sum of n levels, I get the right answer. And I'll show you that now. So this guy, and actually with the help of Michael, we were able to write it in a slightly different form, a more succinct form. So this epsilon y is the inverse of I of epsilon. And you can show by integrating by parts and so forth that it gives you exactly this formula. So this is an interpolation formula between integers, but it's guaranteed to give you the right answer at the integers. And I know it's not a great color here. So this is this S of n here. And this is my integer interpolation. And actually, it gives you the right answer at both the integers and the half integers, right? Because it also crosses 0 at a half and 3 halves, but going in the other direction. I'm not entirely sure of the significance of that. But the important point is I split up my S into a smooth piece, which is this first one, and that's the red line. That sort of corresponds to my I of epsilon. It's what comes from that. But then there's also this discontinuous piece, the sawtooth piece. And you can see the cusps in it as it goes along. And the fact that you have these cusps and so forth is related to this derivative discontinuity. But so the important point is this interpolation formula, which is written entirely basically in terms of I of epsilon, gives you the exact answer, right? So this is pretty elementary. It's just rearranging the furniture. Okay, so we had the harmonic oscillator, right? So I'm going to do some exact illustrations. So for the action for a harmonic oscillator is just epsilon divided by omega. If I choose I to be epsilon over omega, then at the half integers, epsilon will be omega plus a half integer, omega times a half integer, so that's right. And then I just get the inverse, I differentiate it. Well, when I put it into that formula, in fact, because the derivative of epsilon y is a constant, and this average of y, because it's periodic, means from 0 to any integer gives me no contribution whatsoever. So what does that mean? It means that I get the exact formula for the sum of the eigenvalues. And that comes, so the reason the harmonic oscillator comes out exactly is because of the usual semi-classical, whether you do it semi-classically or not, it's the action is just linear in the energy. If you do a particle in a box, you can write down quantum action, when you feed it in, and you get the exact eigenvalues for the particle in a box. You can do the integral, and you get almost the right formula, but it's not quite right for this. This is the sum of n particles in a box. The discontinuous piece now turns out to look like this. The half times this average of y gives you no contribution, again, because integrates to 0 over a period. But the integral of this guy up to n is minus n over 24. And when you put in the exact minus n over 24, it fixes the formula, and it gives you the exact particle in a box. So those were two cases that came out rather differently when we tried to do our energy, our density as a function of the potential before.
These are zero boundary conditions, and it's an infinite form?
Yes. So it's a box of width L, right? So just a little problem in the first chapter of your quantum book. Okay. So this is the partial Teller well, and I've chosen it. So that's this picture here, basically. I've chosen it so that with a well depth d, and notice that you can differentiate this potential infinite number of times. And that's important because we're going to do an expansion in the derivatives of the potential. So that's why we picked this one. And it turns out you have exact eigenvalues for this little problem. So that means it's easy to write down a quantum action. And now it has this square root dependence on the epsilon. And another important feature is that it's a finite well. It has finite depth, right? So you take this formula, you feed it into that formula I showed you, and you get the exact answer for the sum of n values in this well. You can easily check that. So with all these cases, right, we haven't messed up the arithmetic. This formula gives you the right answer. So I would dearly love, well, I wouldn't actually love it, but if somebody has seen this formula before, please let me know, right? And it took us, Michael and I, a couple of weeks to really convince ourselves we had this formula. Right, there are quite a few subtleties involved in it. Okay. Now let's do the semi-classical expansion. So you have this eta, and expand your eigenvalues as a function of eta, and expand your quantum action as a function of eta. And we know how to do that. That's the WKB expansion for the action. The first part, as I said, is just this, the standard WKB piece, and you can do the integral to get the j that goes with that and do all the arithmetic. So zero order. So the WKB eigenvalues are the result. You can explicitly check that it's exactly the same. Doing this sum formula is identical to Thomas Fermi theory for non-interacting particles. So it yields the exact answer for the harmonic oscillator, right? So as we know from semi-classics that the WKB gives you the exact answer, and all sorts of semi-classical treatments are exact when the potential is harmonic. But the equivalent statement in density functional theory is this one here. And there's no discontinuous part. It's a little complicated due to the hard walls and the Maslov index. Okay. So now when you get to the second order, there's a complication, which is important, which is that when you do semi-classics, the second order in the WKB expansion, you start running into singularities near the turning points. So if you just do the algebra, you get the second derivative of the potential divided by p cubed. So the momentum cubed on the bottom gets a little hairy near the turning point. And in fact, so this b is the turning point as a function of the energy. And then I make a little step inside the potential. And there's this piece that has a square root singularity. And when I do this integral, I'll find a square root singularity, and they'll exactly cancel to give me the right formula. Now, the reason this is a complication is because we're interested in functionals. And so it's a bit hard to figure out this kind of stuff as a functional of v. But it turns out, and I think this was inspired by the March and Plaskett paper, you can actually, if you want to look at the integral of I, you can reverse the order of limits and in fact end up with a perfectly well-behaved object. And what's nice about that is now it's once again an explicit functional of v. It has the v double prime at second order and v in the bottom. But see, it's p and not p cubed, and therefore you have an explicit formula, right? Okay, and once you have those formulas, you can feed them into the summing thing, right? And what you find is that so at zero order, there is no discontinuous contribution. The sawtooth guy gives you no contribution relative to the smooth. The smooth guy is growing like crazy. This guy is bounded. But at second order, you can just feed in the zero order action, the classical action, invert it, and you can do this integral. And in fact, if you only want it to zero order, it's dominated by the endpoints, and a little asymptotics gives you this result. And what you can then do is get the change relative to the Thomas Fermi result for the sum of the n levels in an explicit formula, and now the sawtooth guy shows up. Straightforward enough. Okay, but what that means is all the other pieces have come from the WKB expansion. The WKB is an expansion order by order in H bar. When I do the sum of the terms, I get the Thomas Fermi expansion order by order in H bar. So in fact, what you get for the final result is that you get exactly the same thing as doing the gradient expansion as a functional of v plus this correction. And now we have an explicit formula for this correction. And so we had some discussion about the Scott correction and so forth, right? All those are sort of complications due to having the Coulomb potential in 3 dimensions. Here I have a parabolic minimum. This formula is still true even when I have a cusp or whatever, but as a density function, it'll be different. Okay, so I'm doing good. So for this Poschel-Teller well, I made a well with four levels occupied. Here are the sum of the eigenvalues. Remember, I'm counting from the bottom. This is the Thomas Fermi result. This is the error multiplied by 1,000. So these are milli-Hartrees, right? And this is standard performance for Thomas Fermi in 1 dimension. If I do the gradient expansion approximation, I, in fact, don't do any, basically no better, right, in this case. And that's sort of in one dimension. If I'm in 3 dimensions, I will typically do substantially better than Thomas Fermi.
The error seems to have a sign.
Yes, you can analyze all these things. But I mean, the basic, so if I have a slowly varying density, right, in a continuum, I won't have this discontinuous contribution. It's coming from the discreteness of the eigenvalues. And in that case, the gradient expansion will give you the next order correction in h bar. When I put in our correction, suddenly the error has gone down to less than a millihartree.
But let me just ask once again, for example, if I look at the Thomas Fermi column,
Yes.
it says that this is always an estimate, it's a lower bound of the true sum. I mean, the numbers are all positive that you have there.
I think I have the error as being the Thomas Fermi minus the exact. Yes. Yes, I see that it's always positive. Oh, okay. So there are many, many things that we can.
This could be an accident.
Oh, so all those questions one can probably easily answer, right, by taking our normal proofs and applying them to this simple system, right? Almost everything that everybody does that we've talked about can be applied here, probably easier than the derivation that we have, right? So yes, there are many, many things like that, right? And I haven't had time, I haven't had a chance to analyze most of them. But the important thing is the error has gone down by 2 orders of magnitude, right? And in our earlier cases where we had these densities as functionals of potentials in the box boundary conditions where they were working, we saw a similar effect, right? And what it's saying is, for this system, this expansion, sort of this is how good it is. And if I can actually do the 4th order, because I can do it all by hand, is in the micro-Hartree regime, right? And in fact, you can show that this is a convergent expansion in this case, which won't be typically the case, certainly for density functional theory. And we even do better by looking at differences of Thomas Fermi than looking at WKB, although that's not always true. But again, if you look at the differences in energies to 2nd order, you get a tiny correction. And actually, it's the same in WKB or looking at the sums in 2nd order. And even if we look at a very small well, and this is one that just binds, it's actually the kind of well that Dirk was talking about. It's a well depth of 1, and the last eigenvalue is right at the top of the well. And again, we get much, much better results once we put in this correction. And you put in another order, and you get tiny errors. So that's away from the asymptotic regime, but still working extremely well, right? Now, if you'd try to convert this correction into a density functional, and I only did it sort of in terms of the 0 order, the Thomas Fermi density, but what you find is, well, again, if anybody's seen anything like this before, please let me know, because I never saw anything like this before, right? This is, this correction, right? That's what it looks like as a functional of the Thomas Fermi density. That's what it is. And it's like, I put in the Thomas Fermi density, and I get that improvement in the numbers, right? So, like I say in the paper, this has not been devised, it's been derived, right? This is simply the 2nd order expansion, nothing else. I didn't make up any of these numbers. No exact conditions were used in the construction of this formula, right? Except, of course, all of quantum mechanics, right? Okay, I'm going to wrap up. But for me, yeah, you can, right? No. Let me finish and then we can do, right? There are a million questions, right? Yeah, well, this is just obviously, if you could do that in reality, right? I don't think I have time for this, right? But this is just tells you stuff about functional derivatives. There are many, many things. You can read the paper. You can actually understand the delocalization problems. You can even understand broken symmetry solutions when you separate two centers. The situation I've been talking about here is just one center. So where is this all going, right? So this is a little question that came up when Michael and I first started talking. And here's a paradox. So this is from there. If you can find it, there is a paper of Michael and me, right? So some of you who've gotten this paper, it just has my name on it, not Michael's. So it was Michael's framework and teaching me about the semi-classics very, very carefully that made it possible to do this. But Michael says, what do I know about density functional theory? And I say, well, this is really important. And he says, I don't care. And so he didn't want his name on it. He only puts his name on papers where he checks everything himself. And he doesn't know what some of these words are. So he didn't want, it doesn't mean he doesn't like the paper. He likes the paper. It's just not his kind of thing. But this is his kind of thing. Take a parabolic well, right? At some energy. Now think about this. I've told you that WKB gives you the exact formulas for this thing, right? And if we do Thomas Fermi theory, we get the exact answer too, right? But the classical particle knows nothing. The WKB formula, right? The classical particle bounces between 2 points at that energy. It doesn't know what the potential is far away, right? So how can it know the exact answer to the problem, to the energy, without knowing what the potential is? And we heard some mention of this holographic principle, which sort of, I don't think it's a particularly useful principle, but it raises some interesting questions. And the idea is, if you know the density in some small region of space, you can deduce it everywhere. In this case, so the density in Thomas Fermi theory is totally wrong, right? But the energy is exactly right. And of course, what's happening is your harmonic oscillator is an analytic function. If you know it in some small region, you know it everywhere, right? You can analytically continue it everywhere. So in this little problem, what we do is we cut the potential at some point and make it flat. So it looks like this, but with a cut. Now I do WKB, or Thomas Fermi, and I get exactly the same answer because it doesn't know that the cut is there, right? But quantum mechanically, I get a totally different answer. So, and you can do asymptotic expansions for both, right? Both for the unperturbed well and the well with a cut in it. So there's two asymptotic expansions. So this, I think, is about to appear, or it's, online or something like this. I don't know. This is the proofs of this little paper. Now, Michael thinks, well, this little paper, it's not so important. So this is a pedagogical journal, right? I found it pretty heavy going, keeping up with him on this paper, right? But I want to show you a table from the end of the paper. So what's really going on with these gradient expansions, well, first is we've been missing this term, right? And we haven't had a route to identifying it. They're asymptotic for realistic systems. Even if I take a linear potential, it's an asymptotic expansion. So with an asymptotic expansion, as I add more terms, eventually they start getting bigger. So here we do a linear potential. This is just at a WKB level. We're not doing even the sums because we hadn't figured that out. at the time. And here are the first 5 levels in this linear well. And what we do is we do the WKB series. This is, and I haven't truncated the well here, just the linear well. And you look and you find how many terms in the asymptotic series before it starts growing, right? So they all diverge. And this S0 is WKB, which would be essentially the same as Thomas Fermi theory. And S infinity is the exact answer. And you see these are the errors that Thomas Fermi theory makes in these energies. Then if you add enough terms, right, up to the optimal term, which is the standard truncation method, you see the errors that you get there. And you see that sort of for the 5th level, your error is of the order 10 to the minus 8. So this is the power of asymptotic analysis. Your leading term is a sort of 1 millihartree or 10 millihartree error. This is 10 to the minus 8. Then, of course, Michael being Michael, we do hyperasymptotics. And you go in there and you find these decaying exponentials that are subdominant, and you resum them and you put them back in. And look, we can get another order of magnitude improvement. That's the power of the sort of asymptotics that he and many of his students have developed over the last 30 years, right? And there's a very nice article about it in this Princeton Guide to Applied Mathematics, talking about Stokes phenomena and all those things, right? But this is the power. And in the paper that we're currently working on, we started analyzing the asymptotics of these sums. And now, admittedly, he looked at the 8th level. He had to do the calculation to 100 digits of accuracy and found that the error was of order 10 to the minus 50. Which I think is a little smaller than the errors we're used to from our density functionals, right? Okay, so summary. So I've shown you this framework. I think it's a very simple case of something much more general. It gives you this exact integer interpolation formula. It yields explicit expressions for the leading corrections. You have a gradient expansion piece, which is the thing we knew about, and this discontinuous part, which we don't. Inclusion improves by orders of magnitudes. That formula I showed you doesn't look like anything I've ever seen, but it is the formula that gives you that correction. And thanks to many people for helping me with this work. And thank you for your attention. Well,
First slide. You don't scale the chips and potential, right?
that's right.
Can you comment?
What was the question?
You don't change.
I don't change them.
X is not changing with eta.
That's right. That's right.
So why do you have a reason not to do it? Usually d of x, you say when you say in the DFT context.
Well, I mean, that's just sort of, you know, how you set up your scaling, right? It's just trivial scaling, right? So in this case, I did this eta, which is like h bar, because I wanted to show the semi-classics, right? I could do everything exactly the same with the zeta scaling for one dimension that we were talking about yesterday, I think. It's all trivially related, right? And especially in a non-interacting problem. It's right, but it's the same expansion. It's the Lieb-Simon expansion for this in 1D for non-interacting particles. I just picked the choices a little differently. Yeah. Well, sir.
This idea of analytic continuation is probably very powerful. Of course, you just cut the potential, right? There is no information in the original potential piece of this cut, right? But you could possibly try and see if you take two potentials with very different tails, one maybe and the other maybe like this, which are very, very close to the region between the classical points. How much would you actually sense the differences
Well, so these results will, doing just what I've showed here, will have an issue at when you take, say, a double well potential for an eigenvalue that touches the top of the barrier. And as I mentioned, I think on Tuesday, right, or no, but I mentioned it in this paper, this is actually the Coulson-Fisher point in H2, exactly corresponds with LDA to the point where if you pull them apart and where it touches the eigenvalue is exactly where symmetry begins to break. So that's that point, and the bare formulas will have issues there, right? But I showed you also, for example, Raphael's formula for the density and how well it does. So if you analyze the situation for knowing that there's tunneling in between with these you can easily construct formulas that, you know, will be very, very accurate under those circumstances. This is, I've just done the...
To expand on this, I would imagine that the difference in eigenvalues, if you consider these two situations, would be exponentially
Yes.
more than 1 over h bar.
Yes. Oh, yes.
Minus constant over h bar.
Yeah, well, so hold on. So by doing this, the cut, you know, the straight line cut that we do here, right, it has no effect to any finite order. And that's when you call Michael Berry, right? So we heard a little bit, somebody mentioned, you know, oh, is this convergent or is it not, right? So I claim that all these gradient type expansions are asymptotic for realistic cases. And so therefore, and the reason, in fact, you do it in terms of the density instead of the potential is that the density is smoother. And because it's smoother, it means and when you do the asymptotic expansion, the term at which things go bad is one more order typically than they go bad in the potential. And if you think about some of the singularities you see, this is part of that.
Two questions. The first one is just a simple semantic one. So when you said you have the discontinuous contribution,
Yes.
so actually only its derivative is discontinuous.
Sorry?
Only its derivative is discontinuous. The contribution itself is continuous.
Yeah, I mean the effect of the discontinuity in the derivative, right? So all I'm saying is that formula exactly captures what we normally call the derivative discontinuity. So it's, if I had it for an interacting system, it would tell me the delta xc, right? It would be exact for the delta xc.
Which brings me exactly to my next question, and that is that I'm trying to figure out what would it take to get from this beautiful work to, you know, so you can see there are 3 ingredients missing between this and
Reality.
you're right, there's the interaction, there's 1D to 3D, and there's the Coulomb potential.
I think I also mentioned 2 other things. Well, no, I've gotten rid of the box boundary conditions, but I still have to do it for periodic boundary conditions. And there's something else missing as well. I can't remember what. Centers, multi-centers. Yes. So, but the formulas that I showed for doing the summing did not depend in any way on it being one-dimensional. So those formulas should be correct in 3 dimensions. However, if you know anything about semi-classical stuff, you'll know that writing down accurate approximations in this h-bar expansion gets a little harder in 2 and 3 dimensions. Now, a really important thing is, if you look at, say, Michael's papers, of which there are about 500, many of the cases that they consider are either power law potentials or billiard stadiums, because they've been interested in chaos and all that kind of stuff. These are not representative of the problems we care about. The closest thing to we start with something very, very smooth like this, we get formulas that we check are correct. We check explicitly. And now, like one of my students is doing, the linear well. We've done the linear well using the summation formula, and that has a cusp in it, right? And so that formula I showed you for the density functional is different. So one thing I forgot to make a slide about is the Thomas Fermi piece, the local piece, is essentially the same for every system, right? As you go to that limit, it's exactly that simple treatment, right? The correction, this procedure tells you what the correction is, but the correction is different under different circumstances. So, for example, for the surface problem, which we use in making PBE sol, right, you have one turning point, not two. So then the Maslov turns into a quarter, and this changes a little bit. The form of the density functional, the form of the potential functional, I think remains the same.
How would it work for a double well potential?
So that's what I'm saying. I've only analyzed the one center case, okay? So, but I can tell you a little bit about it because that formula I showed. So let me draw a picture. I think I had one on my computer at one point, but I couldn't find it this morning. Well, I can actually, well, yeah, it's better to draw this again. So if this is my I of epsilon for a single well, and I have two well-separated wells, what happens is the exact inexact I of epsilon looks like the following. First, we double this. So looks like that. And what happens is the exact guy will look like this. Oh, have I done? It should go up by, sorry. No, it just goes up by one each time you hit. It runs parallel but steps up by an extra one at every eigenvalue. And then, so if you have I0, which will be an approximation to this guy, when I do the double well, the I0, have I drawn this right? Looks like double, it looks like this guy, 2 times I0. So in this region here, you have this factor of 2 error. Now what happens is, so when you have the double well, right, you have exactly the same kind of ambiguity. So now we have 2 centers. So do you treat the 2 isolated wells as one system? Now, if you're doing normal semi-classics, what you obviously do is treat them each individually. But when you look at this formalism, you can't just double the I0. It doesn't work. So then you have this choice of, do I treat it as 2 separate WKB problems, in which case I get twice as many levels in exactly the right place, or one big WKB problem with 4 turning points, and I get different answers depending on which one I do, which is exactly this broken symmetry situation.
Can you get correct splittings due to tunnel?
So I don't know, because we haven't done any of this yet, right? As I say, I submitted the paper to the archive yesterday or something. But we do know that Raphael's formula gives you those kinds of numbers very, very accurately. So we should be able to make it do that. And I mean, and of course, that's a standard semi-classic problem. But then you could ask whether or not a standard semi-classic solution would be sort of size consistent and all the things we want in the electronic structure theory. So that all has to be analyzed.
Okay,
Absolutely. But that's why I only wrote it for the top. So when you convert it to a density functional, right, there are many sort of different ways you could do it, but if you want to end up like ultimately doing something self-consistently, right, you create a formula which sort of reproduces exactly what that formula does for the Thomas Fermi density. So it doesn't have to be the same as that formula. Yes, so the Thomas Fermi density doesn't exist outside the thing, and you're allowed to have formulas like that, but you cannot for an exact density, which is why I wrote it that way. But then you suddenly have choices, and so I didn't want to put down formulas where I made any choices.
So in some of these standard methods of deriving this gradient expansion in 1D, one gets as the leading correction a negative contribution. And
Yes.
if you choose the wrong test densities, if you
Yes.
then you run into minus infinity.
Yes.
But you don't have a problem like that for your formulation, right?
Well, so let me, I think we have the gradient expansion way back here, right, somewhere there, right. So yeah, this is the minus 1 over 24, right? Well, so this, as far as I'm concerned, this is absolutely not a problem, right? There's no reason in my mind why any of these expressions should be variational. Once I do the h-bar expansion, it's not any quantum system, right? Once I do that. If I take, so for example, this guy, right, I can always do a GGA and do a PADE, put him on the bottom with a plus, right? So that the expansion for a small gradient matches exactly this. I can always do that, and then all of a sudden it's variational, right? This is arbitrary as far as I'm concerned, right? I can do a million tricks like this, right? These are semi-classical expansions, right? There's no reason, as far as I know, that anything should be variational in these expressions. I know that isn't quite the way we think about things in DFT land, but I mean, that's just physics, right? It's,
Let's just have two more short questions. Chuck was the first.
It's a keep going. Okay. I'm not sure whether my question is so short. Okay, so I'm going to the classical problem, right? I have a potential V of x.
yes,
And then I can calculate the classical action, right?
yes,
And I'm putting that equal to an integer and a half of it is the WKB energies. Okay?
yes,
Yeah, right? Now, if I take the derivative of that with respect to the energy, I get the classical period.
yes, yes, exactly. I didn't use those words,
Now
but yes.
we know that if I know the period as a function of the energy,
Yes.
which is the derivative of the action as a function
Yes.
of the energy, that does not identify the potential energy uniquely. There are different V of x's for which I get exactly the same period as a function of the energy. Okay?
Yes.
So even for a harmonic oscillator, there is a different potential, yeah, that gives me the same classical action as a function of the energy, but of course the quantum mechanical
Yes.
energies would be different.
Yes.
Okay? So is
That,
yeah,
yes.
so the WKB energy are the same, but the quantum energies are different.
Right. Yeah,
So
fine.
your formalism would catch that difference?
Yes, absolutely. Yeah, so there's a lot more in the paper than I've said, right? Although it is all rather briefly said, right? So Dunham, 1932, right, shows explicitly that every higher order correction to the action in the harmonic case is identically zero. There is a typo, but in the sign of one of the formulas, but other than that, it's identically zero. And that's only going to be true for a harmonic oscillator. So every other h-bar term is zero. And in fact, now it's much easier with this little trick, right? To, you have to do a contour, it's easiest to do a contour integral to demonstrate that. With this little trick, you can avoid that. But so that's true only for a harmonic oscillator. So when I said that gives the exact answer, right? I feed in the quantum guy, I get the exact answer, but in the harmonic case, the quantum guy is exactly the same as, right? But that's order by order, and all the other orders are exactly 0. Yes, so it's not a problem. Yeah. So yeah, in different parts I was talking about, yeah, different things. Yeah.